Introduction to automotive passive and active rotational speed sensors and the signals they produce. Analog electrical signals have a constant change in voltage over time. Each point along the timeline measures a distinct voltage value. This is an example of an alternating current sine wave with voltage alternating between positive and negative. The digital electrical signal has two values, 100% voltage value on or 100% voltage value off. The computer sees these on-off values as ones and zeros. These ones and zeros are the foundation for digital computer language. When a magnet passes close to a conductor, such as a wire, the magnetic lines of force will cause electrons to move or jump from atom to atom. The movement of the electrons produce a current and a voltage value that can be measured. In this example, an alternating current is being produced. This can be viewed on an analog voltmeter or an oscilloscope. The magnetic induction or passive speed sensor uses a coil of wire wrapped around a magnet. A trigger wheel, sometimes called a reluctor, has teeth on it. The trigger wheel is rotating so that the teeth rotate through the magnetic field that is coming from the sensor magnet. As the tooth passes through the magnetic field, the field bends or fluctuates. The fluctuating of the magnetic field induces a current and voltage into the wire windings. A positive voltage is produced as the tooth enters the magnetic field, and a negative voltage is produced as the tooth exits the magnetic field. The result is a single alternating current or AC sine wave, which is one positive pulse and one negative pulse. If the trigger wheel is rotated faster, the fluctuation in the magnetic field is greater. The result is an increase in voltage as well as an increase in the number of signals that can be produced within the same amount of time. In this animation, the speed of the trigger wheel was doubled. This caused a doubling of the sine wave that was produced within the same amount of time. This live analog speed sensor signal demonstrates the increase in frequency and voltage intensity as the speed of the vehicle increased. Viewing the slow and high-speed waveforms side by side makes the differences obvious. The distance between the trigger wheel tooth and the sensor impacts the fluctuation of the magnetic field. The same number of signals are produced, but the intensity has decreased. An improper air gap will impact the ability of the computer to properly interpret the signal. Air gaps are often fixed, but some are adjustable. If the air gap is adjustable, it will be imperative that it is properly adjusted. The Hall effect sensor produces a digital signal. A voltage source passes through a current limiting resistor. The flow of current through the resistor is controlled by the transistor, which is actually an electronic switching mechanism. The on-off operation of the transistorized switch is controlled by magnetic lines of force. The trigger wheel uses shutter blades to block and allow the magnetic field to turn on and off the transistorized switch. When the switch on the current is allowed to flow, the measured voltage value drops to zero. When the shutter blades block the magnetic field, the switch opens. This stops the flow of current through the resistor. The measured voltage instantly increases to the maximum value. The measured value is either 100% on or 100% off, producing a digital signal. The frequency of the digital signal is directly related to the speed of the trigger wheel. Not all Hall effects use a shutter blade to trigger the transistor. Some use a rotating tooth trigger or a magnetic trigger wheel. This live digital speed sensor signal demonstrates as the vehicle speed increases, the signal frequency also increases without a change in voltage intensity. This animation uses a hydraulic pressure circuit to explain the voltage rise and voltage drop that takes place in a Hall effect circuit. The pump and pressure regulating restriction provides a constant 100% pressure to both restrictions. The number 2 pressure gauge changes based upon the return fluid flow back to the reservoir. If the return flow is blocked by the solenoid valve, pressure on gauge 2 becomes 100%. When the solenoid opens the passageway to the reservoir, the pressure on gauge 2 drops to 0. The 0 and 100% values are directly related to the digital high-low voltage values produced by the Hall effect switch.